Well, let me first say I'm Andrzej Herczynski. I'm from Boston College, and with me here is Arezki Boudaoud, who is a co-organizer of this program. There are a few more organizers who are not here, unfortunately. Well, this program is really alluding, I should say, to a very famous book. It's called On Growth and Form, and it's by Darcy Thompson. And specifically, this book was published in 1917, so we have 100th anniversary of its publication. So this is an immediate sort of impulse for the idea of this program. The title of the program is On Growth, Form, and Self-Organization, and it broadly concerns the issue of shape selection, deformations, and aggregation in various systems, living and dead, inanimate, on various scales. And the idea here is to bring various strands of contemporary research on these topics and open the possibility of collaboration between people who work in different aspects of form in different systems. So there's lots of opportunity for new interactions to be started and collaborations, and to exchange ideas across fairly artificial boundaries that nevertheless define how we work and how we function in the scientific community. And if I may mention some of the topics, this is, as you can see from my answer, a very broad program. But some of the topics are topological aspects of fluid dynamics in various contexts, scaling laws in biology, morphogenesis and growth of tissue, actually growth on various scales, from cells all the way to the organismal growth, propulsion of various animals, for example, various kinds of fish and other sea creatures in water and snakes on sand and things like this, but also collective behavior, for example, swarming of birds and insects, fish schools, and other such phenomena. So this broad program with various aspects of it, and I should add that at the very end of the program we also have a workshop, our fourth of 4 workshops here, which deals with form in art, toys, and games as well. So I touched on this a little bit. First of all, as I mentioned, we have an excuse of the 100th anniversary of this very famous book. But more importantly, there have been new developments in mathematics and also in physics of living systems. And some of those have been fairly insular, are happening in separate communities. One example is a very active area of research in mathematics that goes by the headings of shape analysis and computational anatomy. And this field is about 20 or so years old, but has not yet reached outside of a fairly narrow group of researchers, mostly focused on some mathematical properties, whereas it obviously has, as the name even suggests, computational anatomy, it obviously has implications that are much wider. And this is a good time to allow for the interaction of these mathematical ideas with ideas from other fields. Maybe Arezki can comment more on this.
So one of the main interests of the program is to look at living systems. And so living systems have been studied for a very long time. But now medicine and biology are becoming more and more quantitative, and this allows us to start reconsidering models and testing models with respect to this new quantitative data, and then to get back to the models, improve them, and make progress in understanding how living systems work. So the main mathematical challenge that we're addressing in this program is that of collective effects. How do you move from the behavior of one individual to the behavior of many individuals, or from one cell to that of a tissue or an organism, and how do the different scales of a system work together? So this brings in the questions related to multi-scale modeling of physical or living systems, and there are many issues there to address related to bridging scales, mixing models of different nature, some that are mechanistic, some that are descriptive, as in shape analysis and computational anatomy, some that are partial differential equations, some that are agent-based models. And one big question is how to connect these different models together and use them to better understand the systems that we're working on.
If I may add to what Arezki said, as he just mentioned, one of the challenges is going from individual to collective behavior of systems, from one organism to many organisms. In that regard, one of the topic that has already been discussed in many of our seminars and as a topic of discussion in the halls here at the Newton Institute is the so-called emergent behavior. That is to say, the behavior that emerges when you have more than one individual organism and they interact in some way. There's a famous phrase by a physicist, Philip Anderson, Nobel Prize-winning physicist, which is that more is different. And what that means is that when you study individual particles or cells, you learn something about their behavior, but when you put them together, there's something qualitatively different in their behavior. It's different when you have more. And so more is different is one of the big challenges in this program and in various areas of physics.
And a second challenge is a bit less mathematical, so it's related to how growth and form are connected. And so when we look at the scientific communities, some have been studying how organisms grow or how systems reach their final state. And other communities have been studying the form of and function of their organs or the architecture of these systems. And well, there has been very little crosstalk between these communities. And one of the challenges is to really understand how a system achieves its form and that is appropriate to its own function. And that's what we're trying to address also in this program.
So there are numerous applications, both of the research being done on living systems and on inanimate systems, these sort of two branches of our program. But let me start by mentioning one that is perhaps very immediate and important, and that is in medicine. So this program has one of the strands of this program, one of the themes is, as I've mentioned already, is shape analysis and computational anatomy. And broadly speaking, the idea there is to develop mathematical tools that allow you to measure distance between shapes. In other words, what's the distance between this book, the shape of this book, and this bottle, for example? Is it smaller distance than between these two objects, for example? Now, why does it have a medical implication? Well, think, for example, and this is actually the most important application in medicine to date, about abnormal development of brain, for example. It could be of other tissue, or tumor growth on brain. In that case, by looking at the shape of the brain, you have to decide whether some variation is healthy and normal, or is it abnormal and dangerous? And how do you do this? Well, if you want to quantify this, you have to ask, what is the distance of that shape with this particular variation from what's considered an average or a normal, typical brain? And there are already applications of this. There's, for example, a center for computational anatomy at Johns Hopkins University, where people are working on developing applications to actually clinical work. So this is very promising, still very early, and obviously very important for for studies in health and in abnormal growth.
So in addition to these applications in medicine, there are other applications in biology, in particular in developmental biology. How does an organism reach its final shape? And so moving from the example of brain imaging, there's brain morphology. How do the folds on the brain emerge during your development? More generally, how do forms in nature emerge? The architecture of a tree, the shape of leaves. And when we think of animals, how do they reach their shape? And then how do they move? How does a fish swim? What is its optimal way of swimming to move forward or to escape its predators? And so on and so forth.
And by the way, if I can interrupt, the knowledge gained from these can be then applied to, for example, artificial robotic systems. Say you want to have an artificial fish or something that moves efficiently on a sandy bed on Earth or on Mars. Then one can learn from biological systems.
And similarly, for applications in artificial systems, people are starting to build large groups of robots, swarming robots. So the final applications are not clear yet, but we can get inspiration from living systems, from collective effects in living systems, and understanding them will help us make progress.
Oh, absolutely. Our program is designed to provide opportunities for new collaboration. This is really its raison d'être. It brings people from quite disparate areas. In fact, some of this we've already mentioned. There are here at the Newton Institute some participants who are biologists by training and really do hardcore biology. There are people who are physicists who are trying to understand biological systems, as Arezki, for example. There are pure mathematicians who think in an abstract way about shape and shape deformation and haven't thought, perhaps yet, about the possible application for living systems, for example. So we bring all these various kinds of researchers here, and with the hope that new connections will be made. Indeed, we've observed already quite a lot of new connections between people. By the way, sometimes, a little surprisingly maybe, people who are more or less in the same field but haven't worked together. So I'm thinking of two particular participants from United States, one from Louisiana and one from California, who happen to be sharing a room here at Newton Institute. And they discovered they have an overlapping interest and started to work together. And I think there's going to soon be a real collaborative project and papers coming out of this collaboration. Another funny example is that we've brought here a researcher from Glasgow University and from Arizona who used to work together, but haven't done so for a little while, and they found this a nice opportunity to rekindle their work before. So, and many other examples of new or rekindled collaborations can be given. Maybe Arezki wants to jump in.
So we've also observed many times discussions starting at the coffee machine and between people of very different specialities, and then with exchanging continuing and more serious discussion afterwards. So even if such collaborations wouldn't happen in just now, we can expect people to learn about the other fields during this program and start collaborating together after the end of the program.
Maybe I'll jump in and say something. And another area of impact of our program is in making new connections. First of all, between people who work on various aspects of form in art. I mean physicists who work on understanding form in paintings and in sculpture. I'm one of those physicists. And others who work in related areas of form in toys, or artful toys, and maybe even games. And because these people are, you see, scattered, they're usually in physics departments, they usually have, so to say, a daytime job on working on some problems. And then, as an additional interest, because of their particular interest in art or in music or in toys, they also do some research in these areas, but sort of separately. So with one of our workshops, which will be late in November, early December, we're trying to build a community. So bring these people together and have them talk to each other and realize that they may be working on similar problems. And one related aspect is that we are also organizing an art exhibition here in the Newton Institute. It's actually going to open very soon on the 22nd of November, and will run for nearly a month. And during the last workshop, we will have a session for artists that will speak about art. But the main idea here is to bring together two communities that almost never interact, and that is scientists who work on some problems of form, but also artists who are inspired by science or in some manner address the issue of form or use it in their work. And we're going to have an afternoon where physicists will be milling together right here outside this room with the artists near their artwork, discussing mathematical and non-mathematical aspect of form in the artworks that will be displayed here. So this is a very new connection. I'm very hopeful that some intellectual ferment, will be created out of this.
So, and if we get back to the core of the program, so we can see that there are two classes of mathematicians, physicists, etc. So those who are working on mechanistic models of how form is generated or how form is used to achieve a function, and those who describe form quantitatively, so in the framework of computational anatomy and shape analysis, our next workshop. And the two haven't been talking to each other much, and we expect a few collaborations to arise after the next workshop. And more broadly speaking, so the breadth of this program is very big, well, compared to traditional programs here at the Newton Institute. But sometimes, well, it will be difficult for committees to get together. In other cases, we might expect unusual collaborations to emerge. And we're very hopeful for the remainder of the program.
Actually, I would, maybe partly as an advertisement and partly as an illustration of some of the things Arezki and I were talking about the importance of form. I've mentioned a few times we're going to have a workshop that deals with toys, and I, by pure chance, happened to have in my pocket one of those little toys. It's just a little piece of plastic, but its form is rather complicated and mathematically designed, and it is designed to behave in a rather strange way. By the way, it's called Rattleback, and it can be purchased in toy stores. By the way, the toy stores are places where kids and physicists go to shop, because physicists are big kids. But in any case, if I may show you how this works, here's what it looks like. It's a piece of object that if I rotate it one way, this way, which is counterclockwise from my point of view, it's very happy to rotate, and the plastic is very smooth and the table is very smooth, so it rotates for a long time. But if I try to rotate it the other way, it starts to rattle and reverses the direction of motion. So from clockwise it goes to counterclockwise. I'll demonstrate this one more time. And it goes back. So it's quite an unusual behavior, and the secret is precisely in the form of this thing. So form is paramount. In toys, in inanimate things, and of course in living things, in organisms, at various scales. And this is what our program is all about.